Hello everyone, welcome to Dakshana E classroom program. So in the last lecture we just saw that what is alternating current and alternating quantities. Basically we saw its definition, we saw the generation of alternating EMF, alternating current by AC generator, how it works, how exactly the principle, and then some terminology related to alternating quantities, that is RMS value, average value, peak value and peak to peak value, right? So form factor and peak factors, these are few things we saw. And there is one more thing that is quite important to understand for understanding the AC or alternating quantities and alternating current. So that is phase. I think you must be familiar with this term. So here if I write E is equal to E naught sine of omega t, or in general term I can write phi naught, is it? So if this is some one alternating quantity, or in general term I can write x is equal to some x naught sine of omega t plus phi naught. So this is one alternating quantity that can represent alternating current or alternating voltage. In that case, here we have this quantity, that is phi, we write it omega t plus phi naught. This quantity is called phase of x. So x is what? X is any alternating quantity, then omega t plus phi naught is called phase of that alternating quantity x. It is basically it tells about the magnitude and direction of alternating quantity at any instant of time t. So this omega t plus phi naught quantity, this help us, or you can say tell us about the magnitude and direction of alternating current, alternating voltage at any moment of time t, right? So and we define this quantity as phase. So here we define this phi naught, this is called initial phase. This will be like, or you can write phase at t equal to 0, right? Then there comes another quantity that is called phase difference. Simple terms but quite important here. So here if two alternating quantities I am writing, let's say if alternating current I is written as I naught sine of omega t plus phi 1. Remember the phase difference we will calculate here for two quantities which are having same frequency. The frequency must be same. So this is alternating current and alternating voltage. So that I will write E equal to some E naught sine of omega t plus phi 2. Then the phase difference. So what is the phase of this alternating current? This phase of alternating voltage is this. So the difference between the phase of these two alternating quantity is simply termed as phase difference between current and voltage. The difference in the phase of alternating current and alternating voltage is called phase difference, denoted by delta phi. So here I can write delta phi will be equal to what? Phase difference of current minus phase difference of voltage. So this you can write either phi 1 minus phi 2. This is with respect to voltage, alternating voltage, phase difference with respect to voltage. And I can also write delta phi is equal to phi 2 minus phi 1. This is phase difference with respect to alternating current. Clear? We can calculate even the phase difference when frequencies are not same, no problem in calculation part, but in our syllabus it is limited only up to the case when frequency of both the quantities are same. So we will do the calculation part, we will deal with the things where frequency omega is angular frequency, omega is 2 pi f, f is the frequency, so frequency is same, so we will deal only with those cases. So that is called phase difference, right? And we know the relation between phase difference and time difference. Okay, let me just erase it. Okay, the relation between phase difference and time difference, if there are two possibilities. We may be talking about same physical quantity, maybe alternating current or alternating voltage at two moment of time. Okay, so then two moment of time means there is some time difference arising. This time difference will result in some phase difference between current at two moment of time. That phase difference relation with the time difference is given by this we have seen in wave. There we saw even the derivation how it exactly comes actually. So delta phi is related to 2 pi by t. T is the time period multiplied by delta t. So where delta t is the time difference between two instant or maybe between two alternating quantities, then resulting phase difference due to time difference is given by this. So that is simple relation. Here another important thing is that called Phasor diagram. Let's try to understand it. First simple thing, straightforward, is that in this chapter we will be dealing with alternating current and voltage. Let me make it clear to everyone that definitely neither of these two quantities are vector. They are not at all a vector. So both, or I will write neither of alternating current or alternating voltage is a vector quantity. Both are definitely not vector quantity, but still the simple reason for this Phasor diagram is that alternating quantities are different from DC. So the way we used to calculate net current, net potential difference, net power developed, exactly the way we used to do in case of DC, we can't apply that here in case of AC. So we need some different system, and for creating that system we are using this concept that is called Phasor diagram. A Phasor diagram hai kya? So first thing is just an important point about it is that definitely it's clear that current and alternating current and voltage, none of them is a vector quantity. But what is Phasor diagram? Still, so Phasor diagram is a representation of alternating current and voltage on as a rotating vector or as a vector with angle between them, or basically is equal to phase difference. Is it? Let me write the definition properly. Okay, so Phasor diagram, it's a diagram, or it's basically a diagram representing alternating current and alternating voltage as vector. Remember as vector, and I told it clearly that both of these quantities are actually not vector, but we represent as vector just to make the calculation, make understanding AC or alternating quantities easy. So for that purpose we draw a diagram which treat which represent alternating current and voltage as vector. These vectors are called phasor, with phase angle between them is called phasor diagram. So what is the phase angle? I just told, is it? Phase angle with just like phase difference basically. So phase difference is the phase angle between them is called phasor diagram. Let me just draw it simple. So if I say x1 is equal to some x1 naught sine of omega t, this is my one alternating quantity, and if I say x2 is equal to some x naught 2 sine of omega t plus maybe some phi 1 another x2 alternating quantity. Then to draw these quantities as vector, I will draw it this way. Now the reference, it's up to me, actually we can take either way, but still there are few points about considering reference and which quantity will be taken on x-axis and which quantity will be taken on y-axis. I will write few points about that. So what is the phasor diagram is that if these two are alternating quantities, then I will treat here this x1 as one vector, where I can take this phase as my reference. So I can take this is what reference, where the length of this vector will represent its amplitude, is it? So here you can write length of the phasor vector represent, or you can write is equal to amplitude of alternating quantity. So if x1 naught is the, and here I'm for reference I am taking it, this is my one phase, so this is actually your x1, that is equal to x1 naught into sine of omega t. Now the another x2, what I will write, so this is this length up to here is x1 naught, is it, or x naught 1. Then x2 phasor I will draw, it's what, like omega t, the phase difference between them is this. So the phase, this is angle phi 1, and here this, its length will be your x naught 2, and this is your another phasor, you can write this is x2, that is equal to x naught 2 sine of omega t plus phi. So this representation, this is called phasor diagram of these two alternating quantities. I hope you are understanding this point here. We have alternating quantities which are just like just for like your information purpose, so that you can connect it. In uniform circular motion, we see the projection, is it, on x and y axis, right? So particle moving on circular path, then we see its projection as like SHM, right? And that is actually SHM. So first thing is like SHM is different, but we see its projection like it's circular motion, we try to correct it, is it? Here like similarly with time, this quantity will be changing, this quantity will be changing, so it will be like rotating vectors, it will appear like rotating vectors, but actually definitely these are not vectors. For understanding purpose, to study, to make it easy, we treat them like vector, and this diagram we simply call it phasor diagram. I will draw the phasor diagram for different quantities, and here another point was that you can take this as your reference, then you can take this on x-axis, and then another one you will write it correspondingly. Yes, one more point is that here the angle in anti-clockwise direction is taken as positive. So let me write few points about phasor diagram. So these are few points that will help you in understanding in plotting the phasor diagram for different circuits. So the circuit, these example we are going to see, and I will tell you that how we are like using these properties, these relations, but let me still tell you what are those rules that will help you in like drawing phasor diagrams. So here the elements that we are going to use is the resistor, inductor and capacitor. So in one way we will deal with each of these elements independently, separately, that is like pure circuit, where only one element is taken. In that case, you can draw either one, alternating current or voltage on x-axis. So that is your first point. While plotting phasor diagram for pure element means that is R, L and C separately, either of current or voltage can be plotted along x-axis. No issue is there in that case. While we are drawing the phasor diagram for combination of these elements, the quantity which is common or constant to all the elements must be plotted along x-axis, and the quantity which varies for each element must be plotted along y-axis. So here you can see, while drawing phasor diagram for combination of element, the quantity which remains constant for the combination must be plotted along x-axis. We can see, like, if all these three elements are connected in series, then what will be the constant for all these three quantities? You can easily answer that will be your alternating current. So if circuit elements or circuit is in series, all three elements or maybe even more than and less than that elements are connected in series, in that case your current will be common, it will be constant. So then current must be plotted along x-axis, and when elements are connected in parallel, then you can understand the voltage or the potential drop across them will be common, will be constant, will be equal. In parallel condition, parallel case, parallel combination, voltage or potential difference must be plotted along x-axis and current along y-axis. So these are simple points that can like help you in plotting the phasor diagram. No need to worry, I will plot many phasor diagram. You just try to remember these points and try to check whether I am following these rules, and just learn them and get it familiar, and when it's asked in the problem, apply it exactly same way. It will help you in solving problems easily. So the another point I just told, in series circuit current has to be plotted along x-axis because current will be constant, will be same for all elements, and similarly in parallel circuit voltage should be plotted along x-axis. So these are few points that will help you in drawing phasor diagram. Let me see now next behavior of these circuit elements, first separately, then in combination for alternating quantities, and I will draw the phasor diagram also so that you will be understanding these points easily. Okay, let's see next how the circuit elements, means resistor, capacitor, inductor, will behave when an alternating current or voltage source is applied across them. So let me talk about them one by one. We know when like current is passing through resistor, it offers some resistance, and that resistance offered we may call it or measure it as resistance, right? So similarly in case of alternating current and voltage, what will be that? It will be same or something else. Similarly for inductor and capacitor. So for resistive circuit, consider here one resistance and alternating voltage source is applied. Alternating source of voltage, it's represented in this way. For current also we write it exactly same, and it's because E0 sine of omega t. So let's say this is the source and resistance is R. We do not write here polarity also because you know actually here polarity will keep on fluctuating, changing, so no point in that too. Yes, but for like at one moment I can take the current, maybe let's say going this way, or it will be like going both way, but just to write the KVL I can take the direction of current in one direction just for a movement, is it? So let's say I is the current flowing in this circuit, then by KVL in loop, what I can write? I can write E0 sine of omega t minus IR equal to 0. This implies I is equal to E0 by R sine of omega t, and I can be written as I0 sine of omega t, where I0 is the peak value, that is E divided by R, or E0 divided by R. R is the resistance. So here we can see it's behaving just normal way. Here this is the EMF applied, potential difference, then current we are getting also an alternating current because that will be also exactly varying. here if I draw the phasor diagram, then you can see this is a pure element, pure resistive element. So first thing is we can see the phase difference between EMF and or potential drop and current, it's basically zero. So both will be on same axis. So here I can write, if this is, let's say, E naught sine of omega t EMF, then current will be my this, that is I naught sine of omega t. So both are in same phase. So here you can write the phase difference between I and E is 0, means both current and EMF are in same phase. So that's why the phasor diagram, because there is no phase difference, so I will be drawing both phasors on same axis, x-axis. And this is the peak voltage, this is the peak current, and like you can understand, so the resistance upward to the AC is also just same as it is for DC. So resistance, it will be simply R measured in ohm, no difference, and the calculation for power and etc. I will do that part. So this is how a resistive circuit element will behave for AC. Similarly, let's talk about next a capacitor or capacitor. So here only capacitor is connected across and alternating. I can erase this part. So here consider this situation, one capacitor connected across an alternating source of EMF, E equal to E naught sine of omega t, and again here also polarity will keep on changing time to time, but I am taking, let's say, at one moment of time, at one moment of time, let's say t, the polarity, the charge on the capacitor is this way. C is the capacitance. Then here also I can apply exactly KVL. This implies KVL in loop, and we will get E naught sine of omega t minus, here going this way, Q by C equal to 0, and charge is coming out to be C E naught sine of omega t. So here you can see the charge is also oscillating. And one more thing, we know actually that for a direct current, how like a capacitor behave, you must be knowing that it completely block. And direct current, what I can say, its frequency is equal to what? Infinite, is it? So let me just so this is the like charge, then I can write current through capacitor so that can be expressed I is equal to dq by dt, and differentiation of this comes out to be C E naught. C E naught differentiation of sine is cos of omega t multiplied by omega, so I is coming out to be C omega cos of omega t. Now see here, I can express this, we write it in something like different form. This is E naught divided by 1 by C omega into cos of omega t, and here we write this quantity as xc. This is called capacitive reactance. So you can see this is the resistance offered by a capacitor for alternating current or EMF source. So xc, it is the resistance offered resistance by capacitor for alternating current, or you can write, yes, alternating current. So this is the resistance, and that way I can write I is equal to E divided by XC times, this is cos of omega t. Clear? Okay. So here we are getting something else also, that there is phase difference between arising between current and EMF. E is E naught sine of omega t, and I am getting I. So I can write I is equal to I naught cos of omega t, where I naught is equal to E divided by XE. And see here, XE is what? 1 by C omega. Omega, let me just write it. XE is 1 by C omega, and omega can be written as 2 pi F into C. This is XE. So if XE higher means higher resistance, correct? Here the unit for this is also the XE, capacitive reactance. Its unit is exactly ohm, just like resistance. So this is inversely proportional. So if frequency is high, that means XC will be what? Low, right? Means the resistance that we measure as reactance offered by capacitor for high frequency is low, and resistance offered by a capacitor for low frequency is high. Is it? So XC inversely proportional to F. F is the frequency. This implies for high frequency XC is low, and low frequency I can write XC is high. High XC means high resistance. So what it implies, which frequency it will prefer to pass, which allow easily, is it? When XC is low, and XC is low for high frequency. So this is also like capacitive circuit, also used in high frequency filter or high pass filter. This is also used for circuit designing high frequency filter, or we call it high pass filter. So capacitive circuit block low frequency, like current, you can say it block low frequency, or I will say it's better like offer more resistance for low frequency current. High resistance that we call reactance for low frequency current. Clear? Alright, so that is now its phasor diagram. I hope you understood this. Current, we defining this quantity is equivalent to resistance, but because it's not a resistance, we define a new quantity and we call that capacitive reactance, and it's given by XC. Written unit is exactly ohm. This is the meaning how it we have. XC is higher for low frequency and lower for high frequency. That means XC high means high resistance, that is for low frequency, so it will block low frequency current. So it is used for high frequency pass filter or high pass filter. The phasor diagram, I can erase this part. So the phasor diagram, for that I need to relate the current and voltage. So we are getting E naught sine of omega t, this is the EMF, and I am getting I naught cos of omega t. So these are two different functions. What I can relate, how can I relate? So we know actually this is can be written as I naught into sine of omega t plus pi by 2. Is it? I can be written as, because sine pi by 2 plus theta is equal to cos theta. So this way, now first thing is, this is a pure circuit or pure capacitive circuit. So on x-axis I can take either one, right? So let me draw two phasor diagram. So phasor diagram. So when I am taking current on x-axis, so if I take, let's say this is I naught, is it, cos of omega t, and here what you can see, actually the phase difference between E and I is definitely pi by 2, and which is running forward. So here you can say this is wherever it is reaching, like at t is equal to 0, it's already pi by 2 angle forward. So I leads voltage, current leads. So if I is taken along, then what will be like EMF? This will be like behind by, so this is your E, that is E naught sine of omega t. And if I draw EMF, this I am taking this side, then you can see this is what I is already sine of omega t plus pi by 2. So plus phase, I told in phasor diagram, plus phase is taken anti-clockwise. So from here pi by 2, then it will be this way. So this is I is equal to I naught sine of omega t plus pi by 2. Clear? So here current, you can see here current is leading by phase angle of pi by 2, and see current and voltage potential drop across this capacitor, drawing these things on this circuit, is it, one along x-axis and with the angle between them as phase angle equal to phase angle. This simply circuit is called phasor diagram. So this is the phasor diagram. So now by this time you must be clear that how an capacitive circuit or how an resistive circuit behave when an alternating source, alternating current is connected across them, which one lead, lag, and what it mean actually. So in case of capacitive circuit, these two, both phasor diagrams are exactly correct. There is nothing wrong, and these are very important. Try to remember either one. It's same thing actually, you can remember either one, but it's very important, remember them. Only the another point is, in case of capacitive circuit, your current leads voltage by pi by 2. I can say it in the another way also, that voltage lag current by phase of pi by 2. So this is about how a capacitive circuit behave for an alternating quantity, alternating current or voltage. Let's see, next is inductive circuit. Okay, so here we have one purely inductive circuit, one inductor having inductance L connected across an alternating voltage source. So again we want the relation and all the, like how much resistance or reactance it will offer for alternating current. So the simple thing is, we can go again, let's consider the current is flowing in this manner, and then I can apply KVL in the loop, and we will get E naught sine of omega t minus L di by dt equal to 0, and this implies di is equal to E naught by L into sine of omega t into dt, integration. So this implies I'm getting I is equal to E naught by L, this is omega, integration of sine is minus cos of omega t plus some constant c, right? Now even for inductive circuit, here I check the value of c. So for this circuit also the I average for one complete cycle must be 0, and this implies solving we get C equal to 0. So finally I got the expression for current. It's coming out to be E naught minus divided by L omega into cos of omega t plus 0, and that's gone. So this is clear. Now what it implies, again I can express it also. So first thing is I is equal to minus E naught divided by, we write this quantity as XL, and this is cos of omega t. XL is called inductive reactance. Reactance. Inductive reactance is actually resistance offered, because just listen it. Inductor, what here we are applying a changing EMF. Changing EMF when linked to an inductor. By Lenz's law and Faraday's law, we know that when changing flux will link to an inductor, it will oppose that, right? So whenever something changing flux is linked to an inductor, it will also offer some opposition, and we measure that opposition and we define that, because exactly the point is it's different from resistance. It offer resistance, it offer like opposition, but it's not equal to resistance, because there is no loss of energy, loss of power here, but it still offers some opposition. So we define a new parameter and new quantity, and that we call reactance. So it is like inductive reactance, it's denoted by XL, and it's coming out to be, so XL is equal to again 2 pi, like this L into omega, and we can write it 2 pi f into L. So here you can see also XL is directly proportional to frequency. So means higher is the frequency, more opposition will be there. That implies XL is low for low frequency. Correct? So XL will be low for low frequency. So this implies it will offer less resistance, less opposition for low frequency. So inductor is used for designing low pass filter, means which allow lower frequencies, is it? So, and you can see the resistance or reactance offered for high frequency will be high. So XL high for high frequency. So we can say inductive circuits used to design what? Low frequency pass filter. Correct? That is up to here. So I hope you understand the meaning of XL, inductive reactance. Inductor also offers some opposition, and we measure that in terms of inductive reactance, because it's different from inductor resistor. That's why we are measuring it in terms of inductive reactance. But yes, mathematically and dimensionally, if you look at it, it's exactly similar to resistance. So that's why the unit of this inductive reactance, also unit of XL, is also ohm. It's exactly measured in ohm. And to look for phasor diagram, let me just check first phase difference. So we got E equal to E naught sine of omega t, and I can write is equal to what? This minus E naught by XL into cos of omega t. This can be expressed E naught by XL into sine of omega t minus pi by 2, right? Because sine pi by 2 minus omega t will be cos theta, so minus will be minus there. So this implies I can write this is I equal to I naught into sine of omega t minus pi by 2. What it implies, if you just look at the phase difference, so phase difference between I and E is pi by 2 and which is running forward. So let me erase this part. You remember these phasor diagram, these are important thing. Just wait, after some time we will be using them a lot frequently, so you will require them. So we finally got phase difference between I and E is pi by 2, and by just looking at this you can, I think, easily answer which one is leading here. So you can see here EMF, is it potential difference or voltage? So across inductor voltage leads current by phase angle of pi by 2, or this is also equal to current lag voltage by phase angle of pi by 2. Clear? So this is, now we can easily draw its phasor diagram. Phasor diagram means a diagram where we draw these quantities as vector, and this is again a purely inductive circuit. So means on x-axis either quantity can be drawn. So I'm drawing both the cases. So let's say first case I'm drawing, if I draw EMF on across this, and this is EMF E naught sine of omega t, right? Then what will be where will be your current? So you can see here the current, all right, you can see it here. So current is omega t minus pi by 2, and I told you in case of anti-clockwise, look at it from here, anti-clockwise we take it phase positive, but here it's coming out to be omega t is the reference phase, omega t is the reference phase, and here it's coming out to be minus of pi by 2. So minus means omega t reference, minus means downward, is it? So it will come downward. So that's why your current will be now in this case here. So it's I equal to, you can write E divided by XL into sine of omega t minus pi by 2. Clear? So this is the phasor diagram for purely inductive circuit. Similarly, I can take here current this way actually. So this is what? I equal to E divided by XL sine of omega t minus pi by 2. Now I am taking this complete as reference frame. So now from here, how much it is forward? You can see it is, that is forward by angle pi by 2, phase angle. So then your EMF, this is, you can write EL, and that is E naught sine of omega t. So you can see here EMF or potential difference voltage is leading the current in inductor by phase angle pi by 2. You remember that in resistor current and voltage both are in same phase. In case of capacitor, your, or you can just remember it this way, capacitor inductor things are exactly opposite. In case of inductor, your EMF potential drop, potential difference leads by pi by 2. So in case of capacitor, potential difference lags current by pi by 2 phase. So this is how like each individual elements will behave when it is connected across an alternating voltage source, and we draw the phasor diagram, how much like for which frequency, current, voltage it will offer, high resistance, low resistance, we understood that. So basically you can see here inductor, it's like frequency directly proportional, so it will offer more reactance for high frequency, so it will block that. Is it more reactance means more opposition, and it will allow low frequency, and capacitor will allow high frequency, preferably or easily. So this is how behavior of each individual circuit. Let's see when we are using these circuit elements in combination, then how we can exactly get everything and how things will behave. Let's talk about that. Okay, so up to now we understood the behavior of each individual circuit element for an alternating EMF, alternating voltage source. Another point, next we are going to see if we are using two of these elements or maybe three of these elements, maybe in either series or parallel combination, then one thing is that how problems are asked and how we can answer those problems by studying this concept. Another is like logically we are going that how things are changing, how things like these elements will be behaving, so that we want to know actually. So for that, again, phasor diagram will help you a lot. Remember the things that in case of, this is very important, the phasor diagram for purely resistive circuit, both are in same phase, right? One point. Capacitive circuits, what is there? Capacitive circuit, your EMF lags. In case of inductive circuit, your EMF or potential difference lead current by pi by 2. Capacitive, potential difference or voltage or EMF lags current by pi by 2. So that is another important point is about phasor diagram. I told if in case of series, we will try to draw the quantity on x-axis which is common or constant to all the elements, right? Similarly, in case of parallel, on the x-axis we will draw the quantity which is common or which is constant to all the elements. Okay, see, we have one simple problem here. A pure inductor of inductance 1 Henry is connected across 110 volt 70 hertz source. Find the reactance, current and peak voltage. So this is basic. So here L is given as 1 Henry and frequency is given 70 hertz, and V naught peak voltage you can write 110 volt, and find the reactance. Okay, so now it's a part talking about reactance, inductive reactance, is it? So reactance is given by XL, and that is equal to what? Omega times L, and this is 2 pi F times L. We substitute the value 2 into pi into F is 70 hertz into 1. Simplifying it, you will get 439.6. This is inductive reactance, unit is ohm, right? So B part next is it's asking about current. Then current is given by what? V divided by XL, and that is 110 divided by XL is 439.6. Simplifying, we get it's approximately 0.25 ampere. And the peak value, this will be like I told, given if nothing is mentioned, then it will be the RMS value. RMS value divided by XL will give you the current, RMS value of the current also. So now next part is C. It's talking about the peak value of the current or peak value of current. Current, that is given by what? RMS multiplied by root 2, that is 0.25 multiplied by root 2, that is 0.25 into 1.41, and this is 0.353 ampere. So this is basic application, and we saw actually just calculation of different quantities, reactance, current, potential drop, all these things we can calculate. And we saw up to here how a pure either inductive, reactive or capacitive or resistive element, how it will behave, the phase difference between voltage across the circuit element and the current through it. So we saw, let's see when we have two or more than two series parallel these elements in series and parallel combination, then how we can solve problems coming based on those things, and how anything can be asked, anything can be calculated about such elements. So let me start next with RL circuit. Okay, so let's consider next, that is series RL circuit. Means we here are resistance and inductor both are connected across an alternating source of EMF. Now in this situation, what we can study, what can be asked is about can we apply KVL, how we will apply that, what will be the potential drop across resistor, across inductor at any time, what will be its peak value, what will be the current in the circuit, what is the phasor diagram. So all these things, all similar type of questions can be asked about it. So similarly, like if something is given to you, maybe in the next question, next time, you will be provided the potential drop across the resistor, and then you will be asked to find the EMF of this source, EMF potential drop across inductor. So such type of questions can be framed, can be formed. Now we need to understand how we can answer such questions. Let me help you. So try to understand, try to focus here properly. It's important thing here actually, and it's easy if you understand. If you're not understand, definitely you will find it very difficult. So pay attention here. So simple, this is the circuit, and here I know actually we are like do not mark the polarity of like source, but still let me say at some moment of time the current in the circuit is going this way actually in this situation. So there will be some potential drop across this VR and across this, let me write it VL, correct. And in this situation, if I, let's say if I is the current, is it through circuit, it's instantaneous current, then I can write VR is equal to what? I times R, and VL is I times XL. R we already know, and XL is given by what? Omega times L. Omega is this omega, L is that, right? Okay. Next thing is, the very important thing here is to draw its phasor diagram. Okay. So phasor diagram here, one more point here is that here it's not purely inductive or purely resistive circuit. Here resistance and inductor both are connected, and that too they are in series. So how we will like draw the phasor diagram? We will consider like the quantity which is constant to both on the x-axis or along the x-axis, right? So that will be our current I. So let's say this is I, correct? Then I know actually I and V across the resistor both will be in same phase, so I can write this will be your VR. And what about if I is along this, then what about the potential drop across inductor, whether it lead current or lag current? Then you must remember that, and the answer is it leads by 90 degrees. So that's why I will write VL, this is along VL will be along this way. So now these two are like potential drop across resistor, potential drop across inductor, and they are not simply like along one direction. So the important thing here is that you can't simply add the potential drop VR plus VL and that is equal to V here, source EMF. That is not true here, because there is a phase difference. The point is that I told actually phasor diagram here things are different. Definitely these quantities are not vector, but there is a phase difference. So means they will be treated and they act like vectors, and these answers actually can be solved, these questions can be solved by treating them like vector. So I can write my net potential drop will be across this is your V, right? So now I can write what is V? V magnitude, is it magnitude of potential drop difference net, that you can write V is equal to what? Under root VR square plus VL square. Clear? Now if I substitute these values here, then I will get V is equal to what? This is under root I square R square I square XL square, and this is coming out to be I times under root R square plus XL square. Clear? And here this what I can write here, see now one more thing, I hope you are clear with this term. So this is, let's say some phi is the phase difference between V and I. Now your net, this is the net V, and net V will be what? Like this, equal to this. If I apply potential drop across this plus this will be equal to this. So this will be your along this way. Then I can write my I, the net current through this circuit will be behind, lagging behind by angle, phase angle of phi. I hope you are getting it here. So first thing is I got this. I told for purely resistive element we simply define resistance. For purely inductive and capacitive element we measured a quantity that is called reactance. Understanding? Similarly, if there are resistance plus inductor or capacitor, then the opposition offered, or like you can say we measure, we define a quantity that is called reactance, impedance, right? So impedance it is defined, it is the resistance of an circuit. You can write an AC circuit. So total resistance of AC circuit consisting or containing R, L and C, or maybe R and L or R and C, that can be also. So that is defined as impedance. It's denoted by Z, and again its unit will be also what? Ohm unit, denoted by letter Z. So here this quantity I can write V is equal to what? I times under root R square plus XL square, and this quantity I will write I times Z, and Z is your impedance, so I am getting V divided by Z. So if you are writing like another point, V will be here your magnitude, so this will give you the peak value of the current. Here we can't write it in terms of phase, because phase we need to calculate separately, remember that. So this is also the peak value of the current, or like potential drop. I should write it peak value, here it's V naught, so I should write it V naught, V naught and so on. So this is V naught, so this is, I can write it I naught, I. So I naught is equal to V naught by Z. It is the peak value of current. Yes, if this is peak value, then this will be peak value of current also. Okay, listen it here. If there are few points. If I'm applying KVL in this situation, then I can go V naught sine of omega t minus I'm like potential drop across this, potential drop across this. So remember, there are few things. These quantities are what? These are not instantaneous potential differences across resistance and inductor. We can apply KVL even in AC circuit by considering the potential differences or instantaneous potential differences across different elements. Then it will be perfectly valid. But we do these calculations, these are actually the peak values of potential drop across resistor and inductor in this case. So if you apply KVL, like V naught will not be definitely equal to VR plus VL. That will not be true. Let me write these things in point. So first thing is impedance. I just defined new term, that like here we are getting net, you can say resistance, and net resistance for AC circuit we define it impedance, and this is denoted by Z. So I got this, and it is the peak value of the current. Okay, so if V naught is given to us, Z I can calculate, and Z here it's coming out to be for series RL circuit. So you can write Z is equal to under root R square plus XL square. It's not simple R plus XL, is it? So this is about phasor diagram, and let me write few more points about here. Okay, so here the thing is that V is not equal to VR plus VL. V naught is not equal to, this is not, this quantity is not equal to, we can't apply KVL in this form. KVL in terms of peak value of potential difference is not valid. It's not true. We can't apply KVL in any AC circuit in terms of peak value. But yes, here I will write KVL in AC alternating current circuits can be applied in terms of instantaneous potential drops. Instantaneous in terms of potential drops, we can write KVL. So if I write, let's say instantaneous potential drop, it's VR prime, it's VL prime, and this is V, then I can write, is it? So if VR prime and VL prime are instantaneous potential difference across resistor and inductor, then we can write V minus VR prime minus VL prime will be equal to 0. Then it's valid. I will give you few examples, then it will be like things will be even more clear to you. So the thing is, here things are not just like your DC case, things are here different. There comes another quantity that is very important, that is called phase. Here we can't simply add the net resistance. We can't write simply R plus XL. That is not true. In this situation we are defining a new quantity that is called impedance, and that is given by under root R square plus XL square. So how we calculate? So I hope you understood for this situation. I will tell you another cases also, so you will have idea exactly. We need to take care of phase, and then we will do the calculations just like vectors, actually the resultant vector. Okay, so here we are getting resultant EMF, and that will be definitely equal to the peak value, like net peak value of the source V. So we got this is like V naught, like that we are getting, and here we are expressing this that. So this is the peak value of the current because the phase of current we need to find separately. Okay, so this is up to here. Now let me find the phase. So we got up to it here. So then phase of current, how we will find? See, now this is what the peak value of this, but this is also along the net potential drop or along the potential difference of source. So here I will write this V is along the potential difference of source. So that means if I look for phase, then this direction is what? Along this. You can write this quantity is this, right? Magnitude wise it's V naught, but if I look at it phase, then this quantity like omega t is the like phase. I'm not talking like, so this V is equal to simply V naught sine of omega t. Now the phase of I current is what? You can say it's what? Clockwise, so it will be lagging, right? So then the phase difference between V and or I will write V is equal to V naught sine of omega t and I is phi, and that phi I can write tan phi is equal to what? It is XL by R. We can write it. This implies phi is equal to tan inverse of XL by R. This is phi. Clear? And clearly you can see it from here. Here it implies I, the current I in the circuit lags the potential difference of source. So net current in the circuit I can write now I is equal to I naught sine of omega t minus phi, because it's lagging, remember that. And what is I naught? So I can write I is equal to I naught is V naught divided by Z. Z can be written as R square plus XL square into sine of omega t minus phi. So this way I can express the net current flowing this circuit at any time t can be expressed in this way, and phi is given by this expression. I hope you are getting it. Things are little bit complex, little bit different here. I hope like you are understanding what I'm trying to say here. Here we can't go exactly the way we used to do in case of DC. The system is different. We need to go here with a phasor diagram. We need to, I clearly told you in the beginning itself that definitely current and potential difference are not at all vector quantities, but here when we deal in terms of AC, or in case of AC, they are treated like vectors, because then only we can solve problems based on AC. So that is how. So like in this situation, for this simple case, I tried to get like potential amplitude of, or like peak value of potential drop across resistor, across inductor, and how we can apply KVL. KVL normally we do not write, because if you go with the KVL then things will become a little bit complex. It will be difficult to solve that equation. So that's why it's easier to do the calculation part with, if we are going with phasor diagram. So that's why. But still, if you want to apply, then I told you, you can apply KVL in terms of instantaneous potential drop across each element, but not at all in terms of peak value. Don't apply in terms of peak value. You will definitely get 100% wrong answer if you are doing that mistake. So remember that point. Now I've got like this is valid result because these are instantaneous values. So first thing is, we got already source EMF, this, and phasor, phase difference, impedance, we got the like magnitude or peak value of the current, and by using the looking at the phase difference between source EMF and the current across the circuit, I got the like net current. Now if I know the net current, then I can write potential difference or instantaneous. So I hope you are clear with this. So in this situation, I can write instantaneous potential drop across resistor and inductor. The instantaneous potential drops across resistor. So resistor, it will be equal to what? VR function of time. It will be equal to what? I multiplied by R, and I is equal to this. So it will be equal to V naught into R divided by Z into sine of omega t minus phi. This is VR instantaneous. I hope you are understanding this. We got the net current here. Remember it. VR potential drop across resistor will be in phase with current across resistor, right? Not potential drop across resistor not in phase with the potential like phase of source EMF. That is not true. So you can see VR and I both are in same phase, but not in phase with this. May not be always true. Sometimes it may be, but I'm saying not compulsorily. Right? So that is the point. Remember it. So we have got potential drop across resistor. Now see, you got like phase this current, and already what is VL? Peak value. So potential drop across inductor. So that VL will be equal to what? I multiplied by XL. This will be the peak value. I is equal to what? V naught divided by Z multiplied by XL. This is the peak value. You can write VL, right? But function of time or instantaneous, then I will write, I got like peak value, and it's the whatever the phase current is having, the potential drop across inductor must be leading the current by angle pi by 2. Clear? So that way I can write VLT is equal to, this is V naught by Z. Z I can write either this way also, R square plus XL square multiplied by XL. This is in multiplication, XL times sine of omega t minus phi. This is the phase of current, but voltage across inductor must be leading even current by angle of pi by 2. So this will be your net potential drop across the inductor. I hope you will be remembering the points. There are a lot of things here that you need to keep in mind. Repeat the video if you're still having some confusion, and I hope it's clear up to here. Let's see you next class. Thank you so much.